Hi everyone. So my name is David Igoe. I'm an assistant professor in Trinity College Dublin, and today I'm going to talk to you about my research, which is primarily focused on offshore foundation design. So just to give you a bit of background on myself, so I'm an assistant professor in Trinity since 2017. Before joining Trinity, I was head of offshore engineering at GDG. So I'm still involved in industry with GDG consulting as well. And before that, I worked in UCD as a postdoctoral researcher and then did my PhD in UCD as well. So some of the research you'll see here today is from UCD, and there's also some current projects from Trinity as well. So my research is mainly focused on the main foundations that are used in the offshore wind industry at the moment. So monopile foundations and jacket structure piles, which are kind of the together represent about 90% of what's used in Europe in the last couple of years. So for monopiles, I've looked at lateral monotonic loading. I'll talk to you about the PISA project, which is a very important project, which is helps redefine the industry, I suppose, in terms of monopile design. There's some current projects I'm doing at the moment on cyclic loading and foundation damping as well, which will be very relevant for Irish offshore wind farms. And yeah, so I'll cover these projects. I've also a couple of ongoing projects on pile axial loading, pile aging, which could be very relevant for jacket structures, maybe in the south of the country if jacket piles are used. So to look at the first project, this was a project started in 2013 called the PISA project, and it's, I suppose, one of the seminal projects in the geotechnical offshore wind industry. It was a project run by the UK Carbon Trust, and it was led by Dong Energy, who are now Ørsted, the largest developer of offshore wind in the world. And it included many of the main developers of offshore wind around Europe at the time. So I was involved in the academic work group, which included Oxford, Imperial College and University College Dublin, where I was at the time. The project had a £3.5 million budget and ran over 3 years. And the aim of the project was really to develop new methods that could be used in industry, so engineers would use these new methods to design monopiles, and it's been very successful in that approach. There's two main approaches used. One was a campaign of monopile field tests, which I'll show you now, and there was also 3D FE modelling, which was led by Imperial College. So just looking at the field tests, I was on site for about 6 months between these two sites in Dunkirk and Cowden, where we ran a comprehensive suite of lateral loaded field tests on monopiles. So the figure here in the middle is probably very small to see, but essentially this is the setup we had. For each pile test, we typically monitor about 75 instruments continuously. For the large pile tests that we did, we monitored about 150 instruments, measuring everything from the above ground response to used novel fibre optic sensors to measure the strains in the piles as they were being loaded. And from this, we were able to drive the response of the piles below ground. So these pictures here, the top one is the large pile tests at Cowden. So these are 2 metre diameter piles that were loaded against each other laterally to failure. And the picture in the bottom left there is from Dunkirk. The Cowden site is a stiff glacial till site, which might be relevant for some of the Irish Sea stuff. And we also have a dense sand site, which is also relevant for much of what we see in the Irish Sea. The picture on the right here just shows the monopile foundation response from the field tests. So we've got the horizontal load, so the load that's being applied to pull these piles over on the y-axis, and on the x-axis we just have the displacement of the pile. The black line you see there is the field test results that we measured. The dashed line just underneath it is the 3D FE model that was run by Imperial College, so quite a good prediction of the response from the 3D FE model. And the dotted line along the bottom is the actual industry standard approach at that time. So this is the American Petroleum Institute method that was used to design piles up until this project came about. So you can see the standard method, the old method, the dotted line there, under-predicted the stiffness and the overall strength of the foundation by a factor of 2. It was very conservative, adopted from the oil and gas industry directly. So the aim of this project was to develop new methods which would be much better at predicting the response. And what we have up here on the right-hand side is essentially the new method that's been developed. It's called the PISA design model. It's now the de facto design approach that's used worldwide for designing monopiles. So if you're designing a monopile, more than likely you're using the PISA design model in the last couple of years. Essentially what it involves is doing 3D modelling of your monopile. You can then extract what are called soil reaction curves. These are essentially nonlinear springs. You can just extract them from the 3D model. And you apply them in a simpler beam spring model. So the 3D is very time consuming to do. If you're doing an offshore wind farm design, you might need to run tens of thousands of analysis cases. It's not realistic to do these entirely in 3D. So this PISA model allows you to do the full 3D and extract it and apply it in a very simple beam spring model, which can be run in a fraction of a second to run a single analysis. So you can run tens of thousands of cases in this beam spring model. And the figure in the bottom right-hand corner, this shows the comparison between the 3D and the 1D beam spring model, which is very close. You can get really good predictions with the 1D model as long as they're properly calibrated. So as I mentioned, this project was very successful. We published the papers in Geotechnical at the end of 2020. There was a special issue of Geotechnical, which is the world's premier journal in geotechnical engineering. It's the first time there's a special issue in this journal for about 30 years. So it was quite a big deal. And as I mentioned, it's now the de facto design method that's used for monopile design. And it won several awards, including the BJA Fleming Award, the British Geotechnical Association, prestigious Fleming Award for Best Project in 2019. And it won the gold medal. One of the papers from the PISA project won the gold medal for Best Paper in 2020. So a hugely successful project, and it really shows what happens when industry and researchers collaborate. There's huge benefits for everyone to be gained. So looking at some current research that I'm doing at the moment, this is a SEAI funded study, so the Sustainable Energy Authority of Ireland. I'm doing leading a project on developing damping parameters for Irish offshore wind farms. So this is essentially involves doing some cyclic laboratory triaxial testing on soil samples, where we measure the damping in the soil at different strain rates, at different strain levels, and then we're testing a range of soils which are relevant to the Irish offshore wind sector. So we're keen to work with developers here. If you have any soil samples from a particular site that you want to have tested, please get in contact, and we would love to be able to test them and maybe include them as part of this project. Once we have these soil elements, once they've been tested in the lab, we're going to use them to calibrate constitutive soil models, and they can be that we'll model full foundation response with these soil element tests. So just quickly move on to another project. So this is an IRC, Irish Research Council funded study on cyclic design of monopile foundations. So while the PISA project dealt mainly with the monotonic response, so what is the maximum load you can apply to a foundation before it collapses, cyclic responses are also very important, as offshore loading, environmental loading, is cyclic in nature. So we need to understand how the pile accumulates strain over time, over 25 years, over its design life. And at the moment, there's no industry standard way of accounting for this. So we're developing new methods in collaboration with GDG for developing new methods for doing these cyclic designs. So this is an ongoing area of research that lots of people are working on worldwide. So, and again, this will use 3D finite element models, some macro element models, and we're making some good progress on this. So the results from this should be published in the next 2 years or so. We're also doing some ongoing research at Blessington, so plenty of pile tests. This is like a piling graveyard nearly in Blessington. This is one of our sites. We have 3 sites where we've done pile tests, and they're ongoing at the moment. We're driving more piles in the next 2 weeks there to continue this research. This is some lateral load tests that we did, kind of lower budget than the PISA project, but also very relevant, especially when we come to cyclic design. We also have I'm leading a pile aging study funded by the Geological Survey in Ireland, which is relevant for jacket piles. So jacket piles are much longer and more slender than a typical monopile, and they have been shown to experience aging. So when you leave them in the ground, the capacity of the pile increases significantly over time. So over the first 90 days the pile is in the ground, the capacity might increase by a factor of 2 to 3. And this has been measured at a number of sites, including our site in Blessington. So we're trying to better understand the mechanisms that are controlling this behaviour, so we can include it in design methods, so we can be less conservative in our designs. And then finally, just to finish, this is a EPSRC as a Science Foundation Ireland and the Engineering and Physical Science Research Council. They funded a study called Robocon, which I'm leading the Science Foundation Ireland part of it. And this is to do with developing new in situ tools. So, as it's been mentioned already, the cone penetration test is the most common tool used for offshore geotechnical investigation in situ. So this is essentially will involve developing new devices using advanced robotics, which can help, I suppose, create the next generation of investigation tools. So we'll have things like a PY module, so a module which will laterally displace in the ground and undergo cyclic action, which can be represented for monopiles. And we're hoping this will be a very successful project and be used in the future for offshore design. So this is a project starting in June this year and will run for 3 years. So I'll keep you informed as to how the progress for this goes. But yeah, I can finish on this slide. So just to acknowledge the various funding bodies, Science Foundation Ireland, SEAI, IRC, GSI, as well as a number of industry partners, Roadstone, Lloyds Acoustics, Toronto Piling and TerraDrive Piling. Just to mention that we're very keen to work with the offshore wind industry. If you have samples or if you have research that you want undertaken, please get in touch. All my research is applied. We want it to be used in industry and we wanted to use it to make offshore wind design more efficient. So yeah, please get in touch. We're also trying to make the lab in Trinity, we're trying to get accreditation, so eventually that could be used for commercial testing. So if you're looking to do commercial testing for your offshore project in a few years' time, we should be in a position to be able to help you with that as well. So thanks everyone, and if you have any questions.